Morning, everyone. So yesterday we started looking at potential energy diagrams in a little more detail. Let me just sketch one out for you just for reference sake here. So for a potential energy diagram here, you can label your axis either potential energy, you can plot the x-axis as actually reaction or time, however you like. Let's deal with an exothermic reaction. For an exothermic reaction, our reactants are starting out at some energy. I'm not exactly sure what it is. There's way too many particles, way too many ways energy can actually be distributed among the particles. But I know for an exothermic reaction, my reactants are actually going to become products, and they're going to spit off some energy term. They're going to end up releasing energy to the surroundings. That's what I'm going to feel ending up as heat. So what's happening here is I have my reactants. My products are going to be lower in energy. My system will now be even less in terms of energy. We talked about there being an energy barrier, so that's going to be just the height to the top of the hill there. Just like in that methanol demo, we needed to bring a fire, just a spark, just to get the reaction going. And we started labeling these arrows here. Well, if I plop the reactant line over, I point towards the top. That arrow there was called the activation energy in the forward direction. So you define that in a second here. For the delta H, you'll notice that the delta H could care less what the reaction barrier is. The delta H is just a simple comparison between final and initial. The delta H is just going to be, in this case, a smaller positive number minus a bigger positive number. The delta H actually being negative, which agrees with the fact that this is exo. The heat term is actually being released here. So let me just give you an example reaction, and then I'm going to ask you a few questions. First one, I want you to just define energy of activation, or activation energy. That's another way of saying that there. So define energy of activation and activated complex. So those are the two words. Right. So those two terms there. And then I'm going to specify for a reaction here. I want you to see if you can tell me, identify the activated complex in the following reactions. All right. Let me give you the reactions here. Let's do a H2 and a I2. These react to become 2HI. And let's do a CH4 and a Cl2. This one ends up becoming CH3Cl and HCl. Right. So again, I would encourage you just to pause the video. You can try it out for yourself. Now checking your answer with me here, we're starting off with the activation energy. Activation energy is this E subscript A, energy of activation. This energy activation here definitely refers to this energy barrier. It's this hill. Even though the other side here is more stable, I do want to get to that side there, there's still a little bit of an energy requirement that we want to get over. This energy of activation is, again, you have to use the word minimum. Make sure you have that. It's not just the energy needed, okay? So it's the minimum energy required for, essentially it's for a successful collision, right? Usually this question here will be worded out of 2. I gave you 1 out of 2 for that. You did mention the minimum energy. What's missing here is they want you to add the phrase here, activate a complex somewhere. So instead of just leaving it as, oh, for a successful collision, I want to just emphasize here, to form the activated complex. And just like I'm practicing with you in the next question here, the activated complex is a transition state. It's a temporary species, really high energy, that's at the top of the hill here. And basically, it's just in the process of breaking and forming bonds. So what's important here is make sure in your definition you mention the activated complex. What is the activated complex? I already started alluding to it. Activated complex is a temporary high energy, so unstable, temporary high energy, unstable species. In the process, it's just about to rearrange bonds. So all the particles are present. I'm hoping all the particles are close by the ones that they want. Basically, that means some bonds are breaking while others are starting to form. Right? So those are just 2 definitions there. Definitely, as I alluded to here, make sure you can label these arrows. Activation barrier is always from the bottom to the top. That's why it's always positive number, whereas delta H, depending on whether end or X, so I'm either positive or negative. What about identifying the activated complex? So far for these reactions here, we know we read reactants on the left, these are products on the right. That's sort of like this is R and this is product. But wait a second, our transition state is actually in the middle. It's actually in the process. It's almost like I'm saying the transition state is actually in between. For the first one, we did something similar. For the first one, I have H and H colliding with an I and I. Later on, they're going to end up becoming H and I, right? They've switched partners, H and I, and they can then leave each other. In this case here, in transition then, the in-between is actually going to be when the H's and the I's all happen to be in a close vicinity, where I'm actually just starting to break the bond between H and just starting to create the bond between H and I. That's called the transition state. That is actually the activated complex. Essentially what I do is I just smush the reactants together. We'll still use the square brackets as a notation here. The transition state for the first one I'd say is H2I2. You're going to say to me, well, I've never seen that molecule before. It's true, because this molecule here is very transient. It doesn't actually stick around for a very long time. But all the particles have to be there. Using the same logic here, I can pretty easily just smush together. What about the methane and the chlorine? Well, they have to be close enough together for these bonds here to break. Let's see what's actually happened. Methane here is CH4. It's colliding with two Cls like this. Later on, the CH3 still is present, but now we've created a new bond to Cl, and the H has now created a bond with Cl. So what's ended up happening here, essentially, the H has now bonded with the Cl, and that's created a new bond. I broke this bond here so that I can actually create a new bond between the Cl and the C there. Again, those are reactants, those are products. What's the transition state? The transition state is when all these are smushed together. The order really doesn't matter. I can just say CH4Cl2 or CCl2H4, doesn't matter. But we use that hash symbol just to remind ourselves. This one here is in transition. This one here is, you can't isolate it. You can't collect a pure sample of this because it's a temporary unstable molecule that's just starting to switch bonds here. Today we're going to use another lens here, trying to use collision theory, trying to link it back to potential energy diagrams to relate it back to some of the factors that we saw from earlier in this chapter. So let's just start off here, just rehash here a couple times. As particles collide, right? So what's happened here is I have one particle, it's zipping towards another particle, right? Remember, we've said it a couple times here. The first things that see each other are the electrons. These electrons don't like each other. So what's going to happen is, as particles collide, particles slow down due to electron repulsion. And usually when I draw that picture, people are like, yeah, I know like charges repel away from each other. They do not stop suddenly, right? The repulsion is not that strong. So because they were already speeding towards each other, that's just going to amount to a gradual slowdown. They gradually repel away each other, even though they had a lot of momentum at the beginning. So what's happening here is, as they slow down, they drop in kinetic energy, they start climbing up the potential energy diagram. So from the curve that I just drew up above here, we have our curve like this. Anytime the reactants are actually colliding with each other, they're going to try to climb up this potential energy diagram. Depending on how much energy they had to begin with, that's actually going to control how much potential energy they can actually climb up the hill. They need to have at least be traveling fast enough, at least have the activation barrier, at least have a chance of creating the activated complex to actually get over the hill. So even though this general statement is going to be true, there's sort of two ifs. If too slow, right? If they were too slow to begin with, if you look on that potential energy diagram here, it's not like the potential energy diagram changed. So far we had an exothermic reaction. If I was too slow, sure, I trade in some kinetic for potential. I climb a little bit up the hill, but by the time I've actually collided, there's no more potential energy here. I'm just going to end up sliding back downwards. So in that case there, if they're too slow, they would have collided. They're now in close vicinity to each other. Now it's that very same electron repelling the other electrons here. They hate each other. They want to get as far away from each other as well. So in this case here, as they leave, as particles leave, they speed up. Now for us to speed up, we know we have to have an increase in kinetic energy. Energy can't just be created out of nothing. Where did I get that energy from? Well, I had to have transferred some of the potential back into kinetic, and that's when I actually climbed down the potential energy diagram, and now I'm stuck on this reactant side. I'd say 90% of the collisions, maybe even more, are going to be this, because the particles are actually traveling too slowly. Only the ones that are really, really fast to begin with, if fast enough, so if they have that sufficient energy requirement, basically the same thing. They're going to trade in their kinetic for potential, but they had so much kinetic to actually trade in. The potential energy diagram is exactly the same. We're going to emphasize that in this lesson. The potential energy diagram is the same energy barrier, but it's just because I had so much to begin with, so much money in my kinetic account here. By the time I trade in my potential, I actually gain enough potential that I actually get to the top of the hill. When I'm at the top of the hill, again, I'm going to be very unstable. I'm this activated complex. I'm in the process of breaking and forming bonds. I actually have two choices. At this point here, I can still fall back towards reactants, or I can fall towards products. I can potentially react, and in that case there, we can refer to it as a successful collision. Right? What I want to show you in a little more detail here is we studied the potential energy diagram a little bit. I want to just study with you a little bit of the kinetic energy graph as well. What does a container full of particles look like in terms of kinetic energy? So I'm going to introduce a new graph to you, and then we're going to link it back to this potential energy diagram. We'll call this here a KE distribution. It's a spread of different kinetic energies. And what this one's going to be, we haven't seen this graph yet, but it's going to be plotting the number of particles on the y-axis, and it's actually going to plot the kinetic energy on the x-axis here. Right? So what I'm imagining here is, let's say I have a box full of gas particles, right? We might be at room temperature, right? So at room temperature gives the average kinetic energy. So what's happening here is my thermometer says room temperature is 15 degrees. That's a sample of, if all the particles here are sort of averaged out, that's on average how quick the molecules are going. We're going to look in a little more detail here. In fact, at any given time, sometimes they refer to this as a histogram. At any given time, we will always have some that are zipping around really, really fast, some that are moving around really, really slow. The majority of them are moving at some sort of medium pace. And what our thermometer does for us here is it averages over all of those particles, the fast and the slow. What you'll realize here is the average is going to be sort of the most particles are actually traveling at that medium speed. Let's say that medium speed here is this particular kinetic energy. Remember, we're plotting kinetic energy here. Small kinetic energy here means slow. High kinetic energy means fast. Let's say this is sort of a medium, moderate pace. So what's happening here is if I went up to every single particle and I actually just tracked, how fast are you going? How fast are you going? How fast are you going? I would actually count. Majority of particles are actually going at moderate and medium pace. So what's going to happen here is I'm going to have the most particles are traveling, right? Most particles means, so a high number of particles, this is a low number of particles. Most particles are traveling at this medium pace. I will have some that are really, really fast, some that are really slow, but I'm going to have less of them. So what's going to happen here is I may have only the odd fast particle, the odd slow particle. What we're going to end up with is a distribution. We're going to end up with a slight curve here that does something like this. Sorry, I didn't really run into my dots very well there. But basically, this is a distribution. And essentially what it's saying, we have the majority of particles, even though room temperature gives me the average, most particles travel at some medium speed, at some medium pace. But that's notwithstanding here, there are always going to be some fast, there are always going to be some slower. Now what we're going to do is we're actually going to just try to sketch in the activation barrier. Remember, the activation barrier was from the reactant line to the top of the hill. It was a certain energy requirement that you needed. You needed to make sure that you were coming in with fast enough energy to actually get over this energy barrier. So basically, well, I have energy on this axis here. Basically, there is some amount of energy. That's the requirement here. This is my activation barrier. This is my minimum amount of energy. The particles need to at least have this speed, or else they don't have sufficient energy. They don't have enough kinetic to actually trade in so that they can actually get over the hill. So what it says here is my majority of particles, not only most of them are traveling medium speed, in fact, let's say 80% of the particles here are actually traveling too slowly. These ones here can't actually react because I need to be beyond this activation barrier. I need to be a fast moving colliding with a fast moving to actually react. So therefore, on this diagram here, what I'm actually showing you is only these ones here in the shaded region here, only these particles. So in any given container at any given temperature, it's only your really lucky, really, really fast moving particles. Only these species are moving with sufficient energy. Remember, for collision theory, we needed enough energy and we needed good geometry. It's only these ones that have sufficient energy. So that means most of the collisions are actually going to be unsuccessful, right? Medium collides with medium, they trade in their kinetic potential, they only climb partway up the hill and they get knocked back the way it came. They never really get to this activated complex. It's only the lucky fast moving that actually collide over. Let's imagine that this is plotted. Again, I think I mentioned to you, let's say this is at 15 degrees Celsius, right? Now, usually in temperature, we actually want to put it in the Kelvin temperature, but I'm just going to keep it simple for now. So that's 15 degrees. What's going to happen if I take this container and I now heat up this container? As I heat things up, I know that temperature here is a measure of the average kinetic energy. I basically heat this up, maybe put it in a microwave or stick it over a Bunsen burner, something like that. By heating it up, all the particles are actually going to start speeding up. But now that I actually have this distribution here, not all particles are going to speed up in the same way. What I mean here is we're going to have really slow particles. If I was slow to begin with, by heating up even a little bit here, this is going to speed up by quite a lot, right? Slow particle, a lot of them, speed up by quite a lot. These ones here are more sort of medium pace here. They speed up a little bit. Yeah, they speed up a little bit, right? Maybe not as much as those ones. They already were moving pretty moderate pace. And sort of similarly here, what about these really fast moving particles here? They already were traveling really quick. Sure, by speeding it up, it speeds it up just a little bit, but it's not going to be as much as the really slow particles. So what I'm suggesting to you here is the curve actually gets pushed over a little bit and actually just spreads over this one here. We're going to use a general rule of thumb here. Let's say this temperature here is 25 degrees. So this is T2. So T1 is 15. T2 is 25 degrees here. What's happened here is we've said, let me write this down in words for you so you have it. By increasing temperature, in this case here I just did 10 degrees. I could increase it by however much I wanted. By increasing temperature, all particles speed up, right? All the particles move faster. However, like I'm showing you here, the distribution is going to sort of get pushed over because some particles speed up way more than other particles. So all particles speed up, though by different amounts. Now, the overall number of particles in my container stays the same. So if I took sort of the total number underneath my first curve and the total number out underneath the second curve, the area underneath my first curve should be identical to the second curve here. But what's happened here is because I'm at a slightly hotter temperature, now my thermometer reads maybe 25 degrees. Now my average energy is faster. Those medium particles are moving a little bit faster as well. My medium speed particles are now moving a little bit faster here. My energy barrier doesn't change though. That's the one temptation for people. Oh, when I heat things up, it gets faster. Oh, activation energy gets slower. No, activation barrier has to do with what bonds I'm trying to break, what bonds I'm trying to form. I don't care what temperature you try to do that. The activation barrier actually doesn't change. What you've changed, however, is even though the activation barrier, the limit, you need to be beyond this that can actually react, even though the barrier itself hasn't changed, what we've done is now more of the particles are now beyond the activation barrier. Now this hash region here, I now have more particles that are traveling fast enough that can actually react. So by increasing temperature, all particles speed up by differing amounts. That's what amounts to the curve pushing over. Really make this point here. Activation barrier does not change. Right, you can make a note. Why is that? We still have to, this depends on what bonds I'm breaking and forming. So I don't care whether you are doing this at a really hot temperature or cold temperature, my barrier stays fixed. But why does increasing temperature increase the rate then? Well, we now see, well, it was the only ones that are on the right-hand side of this diagram that can actually react. We actually have more particles. So we have an explanation for this now. Why does increasing temperature? Increasing temperature usually increases the rate. It decreases the reaction time. It's because now we can say we have more particles have sufficient energy to overcome the energy of activation. Right? It can activate so the reaction can go. Right? We have more particles. We see that on the curve here. We're plotting how many particles, we're plotting how fast they are. You notice the area here is actually quite a bit higher. And sometimes they ask questions just as a rule of thumb. They've done some math to this here. How much does the curve get pushed over depending on sort of temperature changes here? Just as a rule of thumb here, for a very slow reaction to begin with, an increase in 10 degrees doubles the particles with enough energy. So therefore, we would expect it doubles the rate. Again, that just comes out a little bit from the math. Basically, I increase this by 10 degrees. I increase it from 15 to 25. I'm expecting this curve here to actually get pushed over. And therefore, because I have twice the number of particles with this activation barrier, I now have twice the number of particles that have sufficient energy. Probably it doubles the chances of the reaction to be successful. All right? So that is the kinetic energy distribution. Your textbook likes actually plotting these two graphs together. Imagine taking this kinetic energy distribution. I had number and kinetic energy as y and x. Let's imagine just sort of rotating it 90 degrees. So I have a number of particles and I have a kinetic energy out this way. What I'm going to plot it against here is actually the potential energy. This one here is just for understanding's sake. I don't particularly like this way of doing it. But basically from our curve here, we had lots of particles are traveling at some medium energy. We had this sort of, there's an activation energy. There's an activation, there's a barrier that you need for particles to be traveling fast enough. And that activation barrier is actually the same activation barrier as we had on the PE diagram. So for example, it was only particles that had fast enough speed that can trade in enough kinetic energy into potential. It's only the particles that could get over the hill that can actually react. So therefore, it's only the particles that are beyond this activation region here. You'll notice the majority of particles here, yeah, I have a lot of them that are traveling at some medium pace here, but these just purely don't have enough energy to actually get over that hill. It's only these guys that do. And when I talked about the shifting of the curve here, as I heat up by 20 degrees, it just shifts over and actually increases the amount of particles that can actually get over the hill. The more particles that I have that are beyond the curve, the barrier itself doesn't change, but I just have more particles that can overcome the hill. If I have a fast colliding with a slow, may not do it, but now I have so many more fast-moving particles, it's a little bit easier for fast molecules to actually collide together. Right? Just for completeness sake here, what if we try to analyze those other features? So the other features that we talked about here, we've talked about generally when you increase concentration. We also talked about that in terms of increasing surface area or even increasing the pressure. Remember, pressure and volume are sort of opposite each other. In that lesson, we talked about doing that generally increases the rate. Remember, increases the rate just means speeds up. You can say decreases the time. So let's think through this here. For a high concentration thing, we have more particles, right? For a high surface area, it's only for heterogeneous. I'll remind you of that word there. They always like asking which factor only applies to heterogeneous reactions. In this case here, for heterogeneous, when I have different states like a solid and liquid, when I'm a large chunk like this, it's only the outer particles that can actually react. What if I took that chunk and I actually snipped it up into a fine powder? In that case, in a fine powder, basically the particles can collide, more particles are exposed, essentially it's a higher concentration. Similarly, for high pressure, low volume here, I'm starting off from maybe a big container, I'm imagining squeezing it into a small container. So even if I have just 4 particles colliding here, being in a smaller container, being in a high pressure, low volume condition, I'm now going to end up having more collisions. What I want to show you in this case, I'm actually not affecting the energy at all. So, although these factors, so the ones I listed, although these factors also increase the rate or change the rate, the KE distribution. The KE distribution, which tracks the energy, does not change. KE distribution does not shift. It doesn't sort of fall over like we did earlier. What happens, however, to the KE distribution, what happens graphically? We start off with this KE distribution. We're plotting the number of particles, plotting off against the kinetic energy. We are at some constant temperature, right? So let's say this is T1. We knew there was some activation barrier, right? This is EA like this. You can make a note to yourself, only temperature can shift the curve, right? Either shift it one way, more particles, or the other way for colder temperature. What concentration has done here is it's just actually increased for us the actual number of particles. Well, since I'm actually plotting more number of particles, even though my average energy is not going to change, I'm still going to be at room temperature for all of my experiments. But as I add more particle, increase the concentration, as I powder it up, as I decrease the size of the container, all I've done here is I've actually increased, let's say I increase more particles in the container, I've actually made the curve taller. You'll notice the curve itself, it's still at the same average energy, right? I'm still at the same room temperature. I'm still at T1. However, just the sheer number of particles that I have also will increase how many particles. This one here, remember we said why it's faster? So when we're under these conditions, more collisions occur. More collisions occur. Don't just leave it like that. We have to link it back to collision theory, although I haven't touched the energy argument. So this one here is more the sufficient energy. Have I actually changed the energy requirement? No. But more collisions occur. You want to link it back to, because I have more collisions, there's going to be a better chance of the good geometry, favorable geometry. So if one collision, not the right geometry, well, another one's coming right away, and when that collision happens, there's a better chance of some of these fast-moving particles. It's only if it's a fast-moving and fast-moving that actually collides together, well, there's more particles that have that fast speed, so therefore, the reaction is quicker. So have another look over your worksheet there, and then just let me know if you have any problems. Thanks, guys.